Good morning and welcome to the final talk of this season. We're already looking forward, of course, to 2019 and another wonderful set of talks and maybe another visit from Alex. I'm Stephanie Marcus from the Science, Technology, and Business Division. And our speaker has been here 3 times. That's more than anybody in the series ever, and this will be the 14th year next year. And 3 times in 3 years. And he is our Mr. Sunshine. He's the, yes. Oh no!
no.
He spilled his water.
Oh, didn't hit any cables, so we're good.
Yeah.
Okay. All right.
I got to get out of here. So Alex is the, what are you, the Associate Director for Science in
That's correct.
the Heliophysics Division. But probably more than dealing with all the data coming in from the various missions, he loves to talk about what he's doing. He's a great communicator. That's his passion. And he and his wife developed a website, which you might want to check out. It's called oursuntoday.org, and it has everything solar.
The sun today.
Oh, sorry.
That's okay.
thesuntoday.org. And I think I will leave. And please welcome Alex Young.
Thank you. Let me refill the water.
Okay.
No harm there. So, I figured it would have been me if it was going to be anybody. So, that's why I didn't want to have too much more coffee. I would start getting shaky. So thank you. It's really great to be here. I love this forum, except for the fact that I have to stand still in front of the podium. But otherwise, this is really, really exciting. And so I encourage you, if you didn't get any NASA goodies, to get some outside, but also to look at the books, the journals. It's a little bit of my stuff, but this is really not about my work so much. Today we're going to talk about heliophysics in general. What is heliophysics? And in particular, we'll also talk about the new mission, Parker Solar Probe, which was launched in August of this year. And I'm not going to tell you too much about it yet. I will get to it. But I want to give you a feel for what heliophysics is, kind of my slant on it, and why it's important, not just for its own science, but for all of the science that NASA does. It actually plays a very unique role in NASA. And because of that, I actually want to start off with some imagery that personally, for me, I think is the most powerful imagery that NASA has ever taken. Some of you may be familiar with this, but what you're looking at is called the Hubble Ultra Deep Field View. And so there was a spot in the sky where if you look up, you don't really see any stars. Okay, even in the blackest, in the darkest areas, there are no stars. But scientists pointed Hubble into that little small piece of the sky, not much more than maybe this big around, and stared at it for a long, long time, many, many weeks. And what they found was this. Everything you see in this image is a galaxy. Not a star, but a galaxy. So 10,000 galaxies can be seen in this little tiny, tiny swatch of the sky. And to think about it, every single one of those galaxies contains hundreds of billions of stars. So these galaxies are kind of like the atoms or the molecules, maybe, in our body, but of the universe. But the fundamental part of these, the fundamental particles, just like the fundamental particles that make up our bodies, are subatomic particles, the fundamental particles here are in fact stars. Billions and billions of stars make up these billions and billions of galaxies. So 10,000 galaxies in this little tiny swatch of the sky. If we look everywhere over the whole sky, we're talking hundreds of billions of galaxies, each containing hundreds of billions of stars. And on top of that, containing billions and billions and billions of planets in each one of those galaxies. More than the stars. So just mind-boggling. So This is, to me, one of the most awe-inspiring images that NASA has ever recorded. But the reason I focus on this is because to get down to the core piece is the stars. It's made up of these fundamental building blocks. And we have something really special. We have one in our backyard that's very close and that we can see in incredible detail. And that's what I'm going to talk about today is our own star, the sun. Now, looking at it from the ground, we get beautiful sunrises and sunsets, but the sun itself is not that interesting when we just look at it from the ground. Now, you've probably heard this, especially during the eclipse last year. You should never look at it with the naked eye without proper filters, proper protection, because it's in fact so bright. And even if we were to say look at it with a camera, we just get this sort of washed out image. Okay. Now, I can look at it with a filter, the same kind of solar safe viewing glasses that we had for the eclipse. And even there, I really just see kind of a yellow ball, a simple plain ball. It's not very interesting, not very exciting. Maybe we might see some little spots on it, some black spots. We call those sunspots. When they're really big, when the sun is active, and the sun actually has an activity cycle, an activity season of roughly 11 years. And when it's most active, you can in fact see some of these sunspots. When you look with the solar viewing glasses, you can see them from the ground. But there is one special time from the ground when we can see the sun in all of its glory, or at least a lot of its glory. And some of you maybe were lucky enough. Who saw the total solar eclipse last year? Now, who saw totality? Okay, wow, that's a lot. That's a good percentage of those who saw the eclipse. This is what we see during that special time when the moon is the same size in the sky, the same apparent size, and blocks the sun out, blocks that bright disk, which in fact is 1,000,000 times brighter than the outer part of the sun's atmosphere. And this is what's revealed. All of that structure, and I so want to just run over there and sort of touch this and talk about it, but all of this structure is real. These are, in fact, magnetic fields coming out of the sun. The same magnetic fields that you can feel when you put a magnet on your refrigerator, that invisible force. But in fact, coming out of the sun's very atmosphere lights it up and traces out these magnetic fields. These are coming out of those sunspots, in fact, because those sunspots we see are these regions of intense magnetic field. And this is what's driving the sun. But that brief moment during a total solar eclipse, we see this kind of detail and structure and get a glimpse that the sun is way more interesting than maybe we thought. But let's step outside of the atmosphere, go up above, and look at the sun with telescopes from space, and we can now see it in even more detail and even more interesting light. There's a lot of light that doesn't make it through the atmosphere, which is good for us. X-rays, gamma rays, ultraviolet, extreme ultraviolet. Our atmosphere is actually quite thick and protects us, but we can't see the sun in those wavelengths of light. And it turns out that's where it really gets interesting. So let's look at the sun from space in extreme ultraviolet. This is what it looks like. Now this is anything but simple and anything but boring. You see there are these flashes that are occurring here. In fact, these bright patches are where the sunspots are. Okay? When I look at them in more energetic light, X-rays, ultraviolet, they're actually bright. They're not dark because they're really hot, and I'll talk more about that. But you see there's a flash, which is a solar flare. It's a sudden release of light. Enough energy is released in that flash to power the world for 100,000 years. Okay? And at the same time, you see there's this flicker across the surface. That's in fact a wave traveling millions of miles an hour. There's a giant blast wave when this flare happens, and it's pushing material away and out into space, billions of tons of material, something we call a coronal mass ejection. It's being pushed out by the magnetic field, and in fact it's just as energetic as the flare. Because it's moving so fast and so much stuff, it actually has the equivalent amount of energy. And this flare, this light, and all that material is filling the solar system. And they're even driving these huge shock waves that accelerate particles to close to the speed of light. And we get these blasts of particles. So all of this stuff is traveling through the solar system. And it's happening to some degree all the time. Little tiny ones are happening all the time, and then every so often we have a bigger one like this. But with these telescopes, I can in fact look at the sun at 10 different wavelengths of light. So here is the sort of simple sun we're used to, just the yellow ball. You do see some sunspots, okay? Now if I can, whoops, I'm supposed to start a video. And it's not starting. There we go. Okay. Now I'm taking little slices and showing you actually other wavelengths, starting with ultraviolet, extreme ultraviolet, all the way up into the very edge of X-rays. Okay. I can take these images simultaneously, and you see that, there's where the sunspots are, but now they're bright. And you see as it moves around how much different the different wavelengths of light, how different the sun is. And in fact, what you're seeing in different wavelengths of light is we go from the surface, which is about 6,000 degrees, up to 10,000 degrees, 80,000 degrees, 1,000,000 degrees, up to about 10 million degrees. So as we go up into more energetic light, we're in fact looking at higher temperatures. But also, as we're doing that, we're also looking higher up in the atmosphere. So this is something really weird. As I go from the surface, which is 6,000 degrees, and move up, it gets hotter. But that doesn't make any sense. I mean, when I go up to a campfire and stand up next to the warm fire and walk away from it, it gets cooler. When I move away from the heat source, it gets cooler. That's what we're used to. Well, that's not what's happening here. On the sun, as you go higher in the atmosphere, it goes higher in temperature. So this is one mystery about the sun that we're going to explore. But what else is going on that's kind of strange? So here's another extreme ultraviolet image. You can see these are those magnetic fields coming out of the sunspots. Again, they're normally invisible, but the sun's atmosphere lights them up. Okay? And all of this material is heating and expanding away from the sun, and in fact flows out into space in what we call the solar wind. So the sun's atmosphere is getting hotter, but it's also expanding away, and it's expanding super fast, millions of miles an hour. It's streaming away. The solar wind is filling the whole solar system. It's carrying away the magnetic field, and it's interacting with everything. In fact, it creates a giant bubble around the solar system. I'll show you a cartoon of this. So there's the solar system, there's the sun, and those particles are streaming away in that magnetic field, and it creates a protective bubble around us, protecting us from interstellar space, all the other stuff out there, and that is the heliosphere. So helio for sun, this is the sphere of the sun's influence. And heliophysics is the study of the sun and the sun's influence on everything in the solar system. Because in fact, all of this stuff, this light, matter, magnetic fields that are streaming away from the sun are interacting with other planets, with their atmospheres, with the planet's own magnetic fields, with comets, asteroids, even the stuff and people we put into space. And so heliophysics is the study of all of that and all of that interaction. Now, one of the aspects of that is space weather. And I'm not going to talk a lot about space weather. I actually gave a talk about that a couple years ago. But space weather is really all of that exciting dynamic phenomena, those solar flares, those coronal mass ejections, and especially how do they influence technology. Because all of this is electromagnetic. And all of our technology, our cell phones, our satellites, are electromagnetic. They're driven by electricity and magnetism. So all of this stuff coming off the sun interacts with our technology. Now, we're very protected to a large extent here on the Earth, and it doesn't physically impact us, but it does impact satellites. It can create a dangerous environment for astronauts. And in the most extreme case, it can actually impact our power grids. So that's one thing that's really important about studying space weather. But we get back to the sun itself. We want to understand the fundamental things about the sun. So the first one being, why does it get hotter as the atmosphere moves away? And why does the solar wind expand away? And actually, one of the things it does is it actually accelerates. It gets faster as it's moving away. So that's another strange mystery about the sun. And then lastly, kind of back to that space weather, all of these huge explosions, I'm going to show you real data of what that looks like. So there's one of those explosions on the sun, material blasting away at millions of miles an hour. And if I zoom away and look at the sun blocking out the bright disk and kind of creating an artificial eclipse, this is what it looks like from space. So there you see that's that material actually unwinding. It almost looks like a piece of string unwinding. Because that's the magnetic field in that material, which is all twisted up, and it's unwinding as it moves away. So all of this stuff from the sun, this energy, is filling the solar system with energy and material. And this is actually one of the most beautiful and obvious manifestations of this. It's the aurora. So when I mentioned that this material and energy interacts with a planet, with its atmosphere and its magnetic field, when that happens at Earth, we get the northern and southern lights. This is seen from the ISS. This is actually over the Indian Ocean, so this is the southern lights. But you see all of those curtains, those are particles that originated from the sun interacting with the atmosphere, and they're causing it to get excited and glow. We have oxygen and nitrogen, which gives us greens, blues, and reds to create this aurora. But this is just one of the manifestations of all of this stuff coming off the sun. Here is kind of what it looks like if we could actually see those particles. We sit in this sea of particles coming from the sun, the solar wind, and then every so often there's one of these coronal mass ejections, which is like, you can think of the solar wind as sort of the background ocean, and then these giant waves on top of it. Those are those coronal mass ejections. And that's what happens when it passes by the Earth. In fact, here you see the particles moving around the Earth being kind of repelled by it a little bit because the Earth has a magnetic field, and these particles interact or are repelled by magnetic fields. Some planets have magnetic fields like the Earth. Some planets don't, like Venus or Mars. And so how they interact is very different and very important to understand, especially, for example, if we want to someday go to Mars and have people on the planet's surface. The environment is very different. But the big point here is that space is not empty. We often hear about the idea of the vacuum of space, with this sort of implication that there's really not much there. But in fact, space is full of all of these particles and electromagnetic fields originating from the sun, interacting with all the different objects. And this is what scientists found out at the beginning of the space age. So 60 years ago, in fact, 1958, a group of scientists led by a man named James Van Allen launched Explorer 1. And that rocket traveled through the outer parts of the atmosphere, very, very high up, through something that we had possibly some ideas about, called the radiation belts. And what we found out was we flew Geiger counters in space, basically, and found out it was full of stuff, full of radiation, and very complicated environment. So there's Van Allen, and this was the beginning of the space age, the beginning of space exploration. And so what that group did is they formed a team to put together a bucket list of what are the big problems we want to solve. Okay. And right about that same time, in 1958, this gentleman, Eugene Parker, published a paper predicting the solar wind. We didn't actually know at that time that the solar wind existed. And he said it did. Theoretically, he worked out what he said were very simple equations. I've looked at them. They're not quite so simple, but he's a really sharp guy. But very fundamental equations, and just sort of worked it out. And it just kind of fell out. A lot of people didn't believe him. He had trouble publishing the papers. But he stuck by what he knew to be true. And he published this paper in 1958, and then a couple years later, sure enough, some future missions showed that yes, solar wind exists, and he predicted it in 1958. And that was the beginning of the space age, and in some ways the beginning of modern heliophysics, and in fact astrophysics. But one of the items on that bucket list of things that scientists wanted to do was to go to the sun. And we had other items like building a giant telescope in space. We have the Hubble. That's an example of the result of that. And there are several other things that were done. So the last item that hadn't been achieved yet was sending a spacecraft to the sun. So why not? Why hadn't they done that yet? Okay, it's 60 years. We've done a lot of really cool stuff. Why not? So this is actually a little analogy by the former project manager for Parker Solar Probe, Nikki Fox, likes to put up to kind of give you a comparison of what was the leap in technology needed to achieve this. And some of you may not even know what that object is on the left. Okay. I think most of you do, but surprisingly, there's a few people that don't. You don't know what it is? No, I know. Okay. All right. But that's a rotary phone, okay, to an iPhone 10, okay? And the leap in technology is almost indescribable, okay? I mean, just the iPhones today are so much more powerful than any computer that we had, a few decades ago, okay, which is kind of crazy. So what are the challenges that we had to get past in order to do this, in order to send a spacecraft to the sun? So I'm going to go through a couple of the technical challenges. This is a mission that has been thought about, and versions of it have existed for these 60 years. So this is not something that was just recently put together. People have been trying to develop plans for this from the beginning. I remember in graduate school going to a conference to see a version of Solar Probe, as it's been called in the past. And I've seen, I don't know how many iterations, there are many tens of substantial iterations that have led to what eventually became called Solar Probe Plus before it was renamed. Okay, and the first part is heat. Okay, and That's actually really one of the key issues is heat. Now, you may think, well, yeah, the sun is hot. Okay, it's really hot. Okay, but it's actually a little bit different than what you might think. So we talked about the sun's outer atmosphere called the corona, that in fact gets to be many millions of degrees. But that's actually not the issue. And I want to explain that because this is a little bit of a difference between the idea of heat and temperature. Okay, temperature tells us how fast things are moving. So when I measure the temperature in this room, I'm actually getting a measure of how fast the air molecules are moving. So when it measures as 65 degrees, that I can actually connect that with how fast the molecules are moving. And the molecules, well, actually there are no molecules, but the atoms and the subatomic particles in the corona, because in fact it's so hot that normal molecules and atoms don't exist, everything breaks apart because they're moving so fast. They're in fact moving the equivalent of many millions of degrees. That's really, really, really fast. Okay, but the difference is in this room, while it might not feel like it, the atmosphere is very thick. There are almost an incountable number of particles in a space like this. So if I think of a box about this size, there are trillions upon trillions upon trillions upon trillions of particles. Some of you may even remember things like Avogadro's number, 10 to the 23s, 6.02 times 10 to the 23. Okay, times a lot. Okay, that's a big number. Okay, so there's a lot of particles here, and there's a lot of particles to transfer heat to my body so I can feel it. But in the corona, in an equivalent size box, there's a handful of particles. Like, I can count them. Maybe 5 to 10 particles in a small box. That's not very many particles. And so even though they're moving super fast, they have really high temperature, but it's very difficult to transfer the heat. Okay. And so the way heat is transferred by conduction, convection, like bubbling water, you see material moving. The other way is by radiation, okay, by radiating energy. Well, that's normally not a very efficient way to transfer heat. But actually here, the sun is really, really bright. And there's a lot of radiation, a lot of light. You can go outside on a sunny day and you can feel how strong the sun is. Well, imagine if it's 50 or more times that. Okay, because you're so much closer to it. So the front of the spacecraft is getting so much radiation, that's actually what's heating it up. So the first part is there's a heat shield that has to be very highly reflective to reflect most of the sunlight away. So that's the first part. But it's also made of a special material, carbon composite, foam and threading that's about this thick. And so the radiation imparts enough heat to the front of the spacecraft that the temperature, the physical temperature on the front of the spacecraft is about 2,500 degrees, okay, which is pretty hot. That's hotter than most substances can exist here on Earth. Behind that heat shield, it's about 85 degrees. Okay, so that's the first part of the technology that was developed. Another one is the solar panels. So you think, well, solar panels is great. We can power the thing by the sun. We're really close. We get a lot of energy. That's awesome. However, solar panels are made of silicon material. If you ever put your iPhone in the car and it gets really, really hot and turns off, okay, electronics don't like heat. So solar panels don't like heat. And in fact, they fold them in when they're really close to the sun, but also there's a radiator system that's cooling it. And these engineers are really clever. They came up with a way to cool using a radiator with just a gallon of regular water. But what they figured out is the way to arrange all this to make it very efficiently take heat away. So that's pretty amazing. And then the last bit that they did, and this also seems kind of simple, but in fact it's not, is the original ideas were, hey, we've got to get close to the sun. It's actually really difficult to get close to the sun. I mean, it's pretty easy to get straight into the sun, but then your mission is pretty short. Okay. I want to fly by the sun. I want to fly through the atmosphere. I don't want to just go straight to it, because then I'm over. It's over. So the problem is that when you leave the Earth, and this is where it's really hard to stay still, but the Earth is moving at many tens of thousands of miles per hour as it's orbiting the sun. And so when I shoot myself off the Earth, I don't just have motion forward, but I have motion this way. So I've got to slow that down so that I don't overshoot. Well, the original idea was, let's use one of the giant planets like Jupiter, okay, to use a gravitational assist to slow us down and then work our way in closer and closer to the sun. But it actually takes a lot of energy to get to Jupiter. So you have to have a huge rocket for that. And a lot of the constraints on how much material, how much rocket fuel and all that were really prohibitive to make this mission cost effective. I mean, you can do anything if you have enough money, but it's not really practical to spend billions and billions and billions of dollars on one thing. Okay, so a very clever scientist came up with the idea of, hey, let's use a smaller, closer in planet, and he figured out how to do it with Venus. So we use Venus to slow Parker down to get closer and closer. And I'll show you what that orbit looks like. So I skipped this image, but that's actually the special unique radiator for the solar panels. So I want to talk a little bit about the distance scales before I talk about the orbit. Now, we're 93 million miles, on average, we're 93 million miles away from the sun. Okay, so how close will we get? Okay, we're actually going to be less than 4 million miles. Now, that doesn't seem like really, really close. But when you think about it in terms of being 93 million miles away, less than 4 million miles is pretty close. It's only a few percent the distance between the Earth and the sun. But I have a nice little analogy to put this in perspective. Okay, so let's think about a football field. Let's think of the sun at one end of the football field and the Earth at the other end of the football field. Now, we're interested in the corona. There's those coronal loops, for example, and those come out to about the 15-yard line of the sun. Mercury is at about the 35. Venus is over on the Earth's 28. Okay, so there are those coronal loops. We want to get close into those to really measure stuff from the sun. We've sent a spacecraft in the past, Helios, and it got close. Okay, within the orbit of Mercury. But Parker Solar Probe is going to the 4-yard line. Okay. That's really close. That's really close. So that's what we have to do in order to get to where we know this interesting physics is happening. What we do know from the studies that we've done remotely, because we've been looking at the sun in incredible detail, but from a distance, with imaging, and you can do a lot from a distance, but there's a point at which you need to go where the action is. Okay, so I think about across the room. I mean, I can use tools to measure temperatures across the room these days. I can learn a lot by, let's say there were curtains over there. I saw the curtains were moving. I could tell you something about the airflow through the room. But there are certain details that I really can't figure out unless I walk over to the other side of the room and actually measure with a thermometer right there and actually measure the curtains in person to see which way the wind is blowing and all the details that I need to do. And so that's what's happening here. To understand why is the atmosphere getting hotter, what are the detailed physics of that, what is the phenomena that's helping to release all this energy and create these solar flares, these coronal mass ejections, this really explosive phenomena driving space weather, and just causing the solar wind to expand away, we know now there's a region where all this is happening, and it's happening right where Parker is going to go. And now we're going to go there in person and be able to physically make measurements right there. We're not just looking at things from a distance, but we're going to measure how fast things are going, which direction they're moving, the details about that environment where all of this interesting stuff is happening on the sun. Okay. So in preparation for the mission, I'm just going to show you some cool pictures. There's a lot of fun stuff that went on. You know, when NASA and NASA's partners prepare a mission, there's an insane amount of testing done on every individual part, on the spacecraft itself. And so these are some examples of the various types of environment testing they were doing. They packed it all up, sent it down to Kennedy Space Center. Then once they got there, they actually put the heat shield on at Kennedy. That was something that's very delicate. They didn't want to ship it together. So this was all put together in a large building, put on top of a rocket, put on top of the biggest rocket we've got, the biggest rocket that NASA has. Okay, it's called a Delta Heavy, and it actually also has a special booster stage. So you got this tiny little thing next to the rocket. It's not much bigger than a small car on this giant rocket with these huge engines, because that's what we need to get this into the orbit we want so that we can start using Venus to work our way in closer to the sun. So that was the original launch window. In fact, the launch window first started on August 11th. The first day, everything was seemingly going well. They have this long checklist. They got to go through everything, and even every item in the checklist actually has tens or more things within those items. Got all the way down, and there was a little anomaly, a signal that said something wasn't quite right. And the window is very short because, in fact, we had less than an hour every day because we're trying to go to Venus. And they were launching really early in the morning because at that time, Venus was the morning star. We're going in that direction. So we had a very limited time period where we could launch it and get it going to Venus. First day, didn't make it through the checklist. Had to recycle. Next day, everything went off flawlessly. So what does that look like? Unfortunately, I don't think I have any sound. Let me see. But I just want you to see what this looks like.
Minus 15. Roll for ignition. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Liftoff of the mighty Delta IV Heavy rocket with NASA's Parker Solar Probe. A daring mission to shed light on the mysteries of our closest star, the sun.
So that was August 12th. It was an amazing day. And so one of the things that's really cool about this, and I haven't talked a lot about it, but Eugene Parker. So let me pause this for a sec. So I want to step back and talk about one of the things that's really unique about this is when NASA launches a mission, typically it has a name, Solar Probe Plus in this case, and then once it's launched, it's named after a person. Okay, that's a typical thing. Hubble, Chandra, all these different missions. But there are always people that are dead, that are no longer alive. This is the first time we've actually named a mission after someone who's still alive. Eugene Parker is still alive. He's 93 years old. He's an emeritus at the University of Chicago, and he was at the launch. So let me show you a little bit more about the launch. There he is. that's his son, and that's his wife. And that's the project scientist. Nikki Fox. So this is the culmination of his life's work. And I'm hoping he'll get to see a lot of the data. Because we're working our way. We've launched, and in fact, it's going to take several years to get there. We make 24 orbits around the sun, each time getting closer and closer. And during that time, we actually pass by Venus 7 times to give us a continued boost to sort of slow us down and allow us to get closer and closer. And I'm going to show you some animations of what those orbits look like, and I'll show you where it is right now. But the cool thing is that we've passed Venus on our first Venus flyby. That happened in September. And then we actually passed by the sun. So we've made our first pass the sun. So it's a little bit bright over here. I'll show you some other imagery. You might not be able to see it too much. But the red, there's the orbit, okay? And there's Venus. So you see, it doesn't encounter Venus every time it makes one of those orbits, but every so often. So let's actually look at, here's what those look like. So the closest approach to the sun is called perihelion, as in sun, helio, okay? And there's the first close approach, which happened starting October 29th. So November 5th was when it was at its closest, on its first close approach. And then you see there was its first Venus flyby. Now, on its way to Venus, one of the things it has, and I'll talk a little bit more about the different instrumentation on there, but one of the types of instruments is a camera that looks out to the sides so that when it's flying by the sun, all the stuff coming out, it can actually image it, visually see it. So they tried out the camera, what we call the first light. So anytime an instrument gets data, even if it's not necessarily taking pictures, we just call that first light. But that comes from telescopes, the first images they saw. This is the first view of the 2 cameras. They have 2 fields of view. That's the Milky Way. But the point is to show you how amazing that camera is, to see all the detail, because it's going to be able to look at these relatively small things streaming away from the sun. It also took another picture. That's the Earth. It's looking back at the Earth. So again, this is the first set of orbits. And so on August 29th, it became the closest spacecraft to the sun ever. And it's just started its mission. And it's become the fastest spacecraft ever. When it makes its closest approach, 3.9 million miles on orbit 24, it will be going close to 450,000 miles per hour. That is almost 500,000 miles per hour, and it's a substantial fraction of the speed of light. So it's an incredibly fast spacecraft. So another aspect of it, not only do we have this unique technology, it's the first spacecraft named after someone who's still living. It's already made these incredible achievements, but it's also the first fully autonomous spacecraft. Now, why is that important? Well, when it's close to the sun, it takes about 8 minutes for light to get from the sun to the Earth. So it takes about 8 minutes for a radio signal to get that far. So when it's traveling by the sun, that heat shield has got to be pointed at the sun, protecting the spacecraft. Any slight motion where part of the spacecraft is no longer under the shadow of that shield would burn up. Pieces of it would burn up very quickly, okay, because it's such a harsh environment. So the spacecraft has to constantly be adjusting itself, and a human being could never do that, because a human being couldn't do it as quickly as necessary in the first place, but we can't communicate fast enough to the spacecraft. So that spacecraft has to be able to take care of herself. So she is fully automated. And this is the first time we've ever done this. So there's a lot of really exciting firsts here. But more important, we are going to our own star. This is the only star in the universe that is so close that we can see it in detail. We can understand it in the fundamental physics that's going on. We can't do that with any other star in the universe. Our star is in fact a laboratory that allows us to study physics that we could never study anywhere else, and we can apply what we know and learn from our star to all the other stars in the universe. It's actually critical. Many of you may be aware that we now have discovered thousands of planets outside our solar system. But in order to really understand those planets and understand the environments they live in, we have to understand the environment created by their stars. And we do that by understanding our own star. So the mission, Parker Solar Probe, is not just a mission about the sun, it's a mission about the universe. It is a key to understanding all of those fundamental building blocks, the stars everywhere. Where are we now? So you can actually go to the Parker website and you can look. So it's kind of hard to see, but you can see where it is on every day. This actually is today's date. I downloaded this today. And you can see where it gets closest, and you see it gets closer and closer, and as it gets down towards orbit 24, there's where it's closest to the sun. Okay, that's going to happen in 2024, year 2024. Happens to also be the year of another total solar eclipse in the United States. So everyone needs to go to that. Absolutely. I'm going to skip this. I wanted to show you this before I get to questions to give you some perspective of what is the spacecraft going to see. Now, you'll see a lot of animations with the spacecraft flying by the sun like it's right there. And it's not actually that close. But over here, this is the sun we see. This would be the sun in the sky, same size as the moon roughly, which is we call a half a degree. That's how big the sun is in the sky and how big the moon is. So if that's the sun we see here from Earth, this is the sun that Parker Solar Probe sees. Okay, 28 times that, 28 times farther across. Okay, and it's incredibly bright. It's going to be flying through those giant loops that you saw, through the region where the sun's atmosphere is to these super, super high temperatures. And all of that activity is coming from. So this is an amazing mission that is going to provide fundamental understanding of our star, of other stars, but also understanding of the phenomena that drives space weather that impacts you and I, that impacts our daily lives. And could potentially, at some point, impact the larger society if we don't continue to study and understand it. So this is a really, really, really exciting mission. And over the next few years, we're going to have, starts off with 2 flies past the sun. I think next year is 3 passes of the sun. And then from every year on to 2024, there are 4 perihelions, 4 flybys to the sun, getting closer and closer. And every time we'll be gathering more and more data, and eventually we'll get to that final goal. And we will continue to stay there as long as the spacecraft has fuel, which should be several more years. We won't get any closer, but we'll stay at that closest. Every time we orbit, we'll be at that closest approach. And we'll continue to get new and exciting information. And certainly, we will learn things that we never had any idea was going to. We're going to find puzzles and questions that we would have never foreseen, because that's one of the exciting things about science, is actually what you don't know and what you don't expect to happen. And I know that's going to happen from this. So I want to stop there, and then I've got some time for questions. But I hope you got to have a good feel for kind of what heliophysics is about and the beginnings of how we're coming into sort of a new age of understanding the environment, the space we live in, and how our star drives that. Thank you.
Thank you very much. I understood that, so that's maybe a first. Thank you. But aren't you getting some data tomorrow? The first data? I thought I read that.
Yes, the science team will be getting some new data coming up, and there will be a press conference next week. So next week is the American Geophysical Union meeting, which this year will be in DC. It's an exciting year. So this is an exciting year for a lot of reasons. It's the 100th anniversary of the American Geophysical Union. It's going to be the first data from Parker. This is 60 years after the beginning of the space age, 60 years after his fundamental paper, and 60 years after the founding of NASA. So this is a really, really, really exciting year. And I'm not even talking about Apollo, because we're also getting some anniversaries with Apollo. This year is the anniversary of, and we've just had it, the anniversary of Earthrise. The first time we saw the Earth rise up over the moon from space, and it gave us a perspective of our planet in a way that we've never had before. We saw it as a planet. We saw it outside of it. And that is one of the pivotal moments about our perception and perspective of our place in the universe. So it's a really exciting year. A lot of cool stuff. So yeah, next week we'll be seeing some first results from Parker. And I didn't go into the details. There's going to be a lot of stuff about the different instruments, but there's a whole suite of instruments. I showed you the camera, but there are instruments measuring the temperatures of particles, high energy particles, kind of the background particles, all of the electromagnetic fields in the environment, all these different parts of what that environment is like. These whole suite of instruments will be giving us lots of different data to tell us what it's like, not just visually, but with lots of detailed fundamental information. Okay, so I've talked again. Questions in the back?
So what is the probability for failure of the mission, and what are the most probable failure outcomes, I guess?
So what is the probability of failure, and what are the most probable outcomes? Well, okay, so this is getting into something. I am not a systems engineer. Now, I'm not gonna, so I can't give you any hard numbers. I will, actually I have some colleagues here that maybe can back me up on things who know a lot about missions. So I'm looking at you, Lou. But let me just say that the simplest way to put it is that these engineers have gone through every possible scenario and situation that they can have any control over. There are always things that could happen. You know, there can be failures in equipment and electronics, but again, these things are tested and tested and tested over and over again and certified, and especially they all have a legacy of being used on a lot of other missions. And I will say a lot of the technology that's used on this spacecraft has been developed in the planetary community, which has incredibly harsh environments, especially around places like Jupiter and Saturn, okay, which in some ways are even more harsh than the sun. Not all of it. The actual physical light is much higher in the sun, but the particle environment, the radiation environment is really, really severe. So it doesn't give you a specific number, but the chances are incredibly slim. Now, if something were to happen, there are backups, there are contingencies for spacecrafts to handle a lot of different situations. I have worked with many different missions where some instruments have failed, or some instruments, part of instruments have failed. That doesn't mean the whole mission is over. It does change the science goals, but in every case that I have worked with, and I know this is true for most missions, it does not stop us the substantial amount of science that's coming in from it. Okay, it may limit some of the higher end goals, but the overall goals have always been achieved in these sorts of missions. I don't know if you have any additional things you want to say, Lou.
Well, the space radiation environment is probably the key.
Yeah.
The electronics are radiation hardened to be able to withstand the particle radiation of space. The other thing is that if the pointing mechanisms, if the gyroscopes were to fail, and that heat shield wasn't to be just exactly in front or between the instruments and the sun, that could be a problem. But that's equally unlikely.
Right, but that would be the most critical thing. Would be pointing being off, and the instruments not being behind that heat shield. Now, one thing I will say about this, there are some unknowns here. We are going to a region of the sun we have never been to before. It's also a region that we can't see certain things. There have been discussions about populations of small bodies and things like that very close to the sun that are speculated to exist, but we can't see them because it's literally too bright. We try to see them during eclipses, but we don't really know the details of that environment around the sun within the orbit of Mercury. So there could be potential issues there. So not quite as definitive an answer as I'm sure you'd like, but So you had a question, sir?
When it reaches its closest approach, will that be its stabilized orbit, or will it decline more over time? And what would its apohelium be?
Well, when it reaches that orbit, it will stay in that orbit even after the mission ends, and it's no longer pointing. It will start to break up as a cloud. But orbital dynamics, that cloud of space stuff, will continue to orbit the same orbit. It will eventually deteriorate, and actually eventually become part of the corona itself. It will sort of be absorbed by it. I don't remember exactly where the apohelion is. I'd have to look on there. It's roughly around the distance of Venus. Okay, if you look at the orbit, you see it's roughly the distance of Venus, and then Venus is moving much faster.
So it's going to be fairly eccentric.
Yes. So it will keep pretty much the same orbit that it has on that last closest approach. It will continue there while it has fuel, and then even after it runs out and its pointing is off, it will stay in that orbit, basically. Yeah. So there was a question there, and then I'll go to you.
In Voyager 1 and 2, they said that they've kind of passed the heliosphere now where solar winds are 0 miles per hour, or very small or non-existent. What does that mean when you talk about solar winds, and what impact would that have on the...
Well, so you mentioned Voyager 1 and Voyager 2. So that's actually you bring that up is really good. That's another sort of monumental thing about this year. Voyager 1, we believe, has already left the sphere of the sun's influence, and now we believe Voyager 2 is close to, if not already left it. It's not a definitive place, but a region. But that is basically where we are outside of the primary influence of the sun, and we start to see the influence of the interstellar medium and changes in the cosmic rays. So the universe is full of these particles called cosmic rays, which are coming from supernova, exploding stars. The sun and the heliosphere actually pushes those particles away. It sort of acts as kind of a shield to deflect some of those particles. When the sun is most active, when the solar wind is at its peak, it's pushing more out and pushing more of those particles out of the solar system. And then when the sun is less active, there are more of those particles getting in. So we're seeing the changes as it moves outside that boundary. Does that answer your question?
And what else, when they say 100,000 miles per hour, what are they talking about in terms of solar winds?
So I mean, it's like, what is the solar wind that it's encountering, or?
I just referenced that speed, that they're actually 100 miles per hour solar winds.
I guess I'm not quite sure. Not quite. You mean the solar wind out at the boundaries? Is that what you're referring to?
Yeah.
Well, that's just sort of.
The source was the sun.
Yeah, the source is the sun. So this all of these particles are continuing out from the sun. And then they eventually start to slow down and they reach this boundary. And that's kind of where the solar wind is no longer substantial, no longer has any influence. So I'm not sure if I'm answering.
Yeah, that's it.
Okay, all right.
Alex,
Yes.
sure to repeat.
Oh, okay, I'm sorry. So yes, sir.
Yeah, someone kind of answered my other question, but I wanted to ask, how is Parker, I guess, going to help us understand why certain, I'm not sure if it was solar winds, but you said something kind of accelerates even after it leaves the sun?
How is Parker going to help us understand why the solar wind accelerates? I think. Well, so the solar wind, because the atmosphere is heating up and expanding, the solar wind naturally expands. Okay, that's just a natural part of the atmosphere expanding away. But what's happening is in this region where Parker is flying through, it doesn't just expand normally with what you expect. Now, the big mystery is, why is the atmosphere hotter? Okay, once we know that it's hotter, let's not worry about answering that question. The fact that the atmosphere is hotter, we know that it should stream away. Okay, that's going to happen. But what is weird on top of that is that not only does it stream away with what we expect from those million-degree temperatures, but it in fact accelerates. So it's expanding from the sun, and then it speeds up. That's weird. Okay, and so that's the part where what we do know from other types of observations in theory is there's something happening with the magnetic field of the sun. Okay, something is happening in the solar atmosphere due to the magnetic field that is causing those two things to happen. But we don't really understand the details. So that is why Parker being there, actually being where this is happening, where this acceleration is occurring, is critical. So being, again, as I said, where the action is, Parker will be making fundamental measurements which answer the questions. We have ideas, we have a set of competing theories, but what we need to do is pin it down. Okay, so it's not that we don't have any clue. That's not the case. We have clues, but we need some more pieces to that puzzle, and we are certain that what we're going to learn from Parker, from being where this stuff is happening. Actually, I'll get to your question real quick. One analogy that Nikki Fox likes to use is, if something happens upstream, like somebody drops a pebble in the water and there's a ripple coming down, you're farther downstream, you see a ripple, you see something happen, but you don't really know where exactly did it happen and what are the details, what was the shape of the rock that made the ripples and this sort of thing. So going to where the pebble is being dropped into the stream is telling us more than just seeing the resultant ripples down the way. Does that kind of make sense? And I think that's really the key of what it's going to provide for us. Yes, sir.
Question about the timing of the mission,
Mm-hmm.
or the scheduling of it. Did it matter at all where we are in the sunspot cycle?
Okay, so the timing of the mission, does it matter at all where we are in the sunspot cycle? That's actually a really good question. The immediate answer is no. Now, yes, it matters because we have to think very, very, we know that all this radiation on the spacecraft is actually pushing the spacecraft. Okay, there's actually pressure from the solar wind, from the radiation. So where we are in the solar cycle means that we have to make adjustments. So it's sort of like you're going outside, you're riding your bike, and it's windy. And you know if the wind is blowing this way or the wind is blowing that way, you have to adjust how you're riding the bike to make sure you don't get blown over, or if you have to speed up. So knowing that is important, but overall, does it matter that it's windy? No. That's actually okay. We just, for the planning, we would need to take that into account. But it's actually exciting. We're going to be getting to the closest approach near solar maximum, and that excites scientists because having one of these big eruptions go off while we're there is really going to be a beneficial thing. It's actually going to provide you new and unique information. Yeah. Yes, ma'am.
Are these images going to be able to be seen in ultraviolet, extreme ultraviolet light, just visible light?
So are these images going to be seen in other wavelengths besides visible? This particular instrument that I showed you, that is only visible. So those are only visible light images. Yeah. They had to make certain decisions about what they were going to put on board, given the limitations. You know, stuff is expensive to put into space, and the heavier it is, the more there is, the more it costs. And so they just had to make some science decisions, and they decided that ultraviolet, extreme ultraviolet images were not necessary for what they wanted to do. Yes, sir.
Relative to the poles of the rotation of the sun, is the probe always passing the same points on the surface as it goes?
It's not passing the same points because the sun is moving. It actually rotates faster at the poles than it does above and below. But there will be no same. Well, first of all, because it's not a solid body, there's going to be no features or structures that will last substantially in any one place. So it's not really going to be coming back to the same spot. It's all going to be kind of mixed up. Now you can see large sunspots come back around. They'll change and they'll be in similar proximity, but it would just be total coincidence if you actually hit one. I'd have to look at the actual timing, but they're not really in sync at all. Yes, sir.
I don't really know how to ask this because I'm not as smart as you are about it. But you were talking about temperature and the number of particles in a box of like atmosphere versus out there.
Mm-hmm.
So what I'm wondering is these prominences that fly off from the sun are so hot.
Mm-hmm.
What would be their temperature like as they get to the Earth, as they pass the Earth? Are they still really hot, or do they lose a lot of heat, or whatever the energy is that they have?
That's actually a really good question. So when these structures, these prominences, and which we call them coronal mass ejections when they leave the sun, are they still hot when they get here? They are. Okay, the structures actually have magnetic fields, their own magnetic fields that break away from the sun. And so when you see this big blob of stuff from the sun, these coronal mass ejections, they actually have their own internal magnetic field. Okay, so they have internal structure. And they do still have, that internal structure does keep this energy, some energy. Is it as hot as it was when it was on the sun? No. But are those temperatures still hotter than sometimes the ambient solar wind? Yes. But the temperature scales are much different. But yeah, there is some energy that's kept inside of that structure. But the other thing is that structure has expanded. Those things expand very quickly. Even when you saw that video that I showed of that thing unwinding, by the time that thing had unwinded in that image, that actually was several times the size of the sun, just in length. So they actually form these clouds that fill the entire inner solar system. So the temperatures are nowhere near the many millions of degrees that you see in the corona. But there is still a lot of energy there. And they also contain kinetic energy. So anything that moves has kinetic energy. The more mass there is and the faster something is going, the more energy it has. So given that these things are so massive, so huge, and they're traveling at many millions of miles an hour, they have a lot of internal energy in them. And we see that. We actually physically see the Earth's atmosphere and the Earth's magnetic field shake when these things hit the Earth. In fact, that shaking is what is ultimately creating the aurora. One of the things, a fundamental thing in physics, is if you have a magnetic field and you move it very quickly, it generates electrical currents. That's actually the principle behind a generator, for example, or a motor. So when that coronal mass ejection comes and hits the Earth's magnetic field rings like a bell. So that magnetic field is moving, and it generates currents in the upper atmosphere, and those drive the particles which give us the aurora. When those currents are really strong, and we actually have a very strong solar storm, it builds currents on the ground and can knock out power grids. That's the concern for large space weather events. So these things have a lot of energy. A lot of energy, yeah. Yes, sir.
Regarding the solar wind, you had an illustration early on that showed what appeared to be something of a current flowing over the solar system, where it buffeted on one side, but it was kind of strung out on the other. Is that our solar system moving through the universe, or is there an actual external current? And just a quick unrelated question: was there any accommodation made for keeping it from crashing into the Elon Musk's Tesla?
So I'll start with your first question. Was there any a second question? Was there any accommodation to keep from crashing into Elon Musk's Tesla? I'm sure there was, because I really don't think they wanted to hit a car with $1 billion spacecraft. I don't think they really cared so much about the car. I can say that. Given that there are hundreds and hundreds of people that have spent their lives working on this, that would really, really be bad. So, and I've seen spacecraft and had colleagues whose spacecraft blew up and things like that, and that's not a pretty sight. So, so your other question. So, hey, you said I had an animation or
It showed that the solar system, that the solar winds were buffeting on one side.
okay. So the animation that I had about the heliosphere, and so what is your question about that?
Is there actually an external current, or is that our
Yes. So is there an external current? Okay. Let me find that quickly. Do I have time? Okay.
I'm just curious if it's coming from a specific source.
No, that's actually a really good question. So this one?
Yeah.
Okay. Yeah. So what you're seeing there is, well, what the movement of it is trying to illustrate the change in the solar cycle. Okay, so the solar cycle, the sun goes from low activity to high activity back down to low activity over 11 years. And so what you're seeing there is the breathing of the solar system, breathing of the heliosphere. When solar activity is high, it's puffed out, and when it's low, it kind of pulls in. And so that's what that motion is. But all this stuff, this heliosphere, is traveling itself through the interstellar medium. So this is like a ship in the water, and the fact that this stuff is pulled behind it, it actually makes it makes a wake, because that whole system is traveling through the galaxy, and so it's traveling through this interstellar material. But it's very, very, this is very simplified. It's actually much more complicated than this. It's not this even simple spherical structure, because it's being dragged back. And you see the same thing with the Earth. The Earth has a magnetic field, and if it was just sitting still, it would be kind of a nice symmetric shape. But in fact, the Earth, because it's moving around the sun, has this long teardrop shape, the magnetic field, because it's being stretched by the solar wind. So planets and solar systems all do this sort of similar thing as they're moving through different material in their environment. Yes, ma'am.
Do you have any instruments on board that record sound, like solar wind?
Do we have any instruments on board that record sound? Well, in a way we do. So, sound is just compression of the air, and or the compression of water, compression of metal, any of those, a compression of material is a sound wave. And for us, the compression of the air is picked up by our ears. But there are waves of these materials. You know, we're traveling through these materials, and there are waves generated, and we are measuring those waves. We do have instruments which will measure them. They could, in fact, be turned into sounds, and I know that they will. People do something called sonification. Actually, we're interested in that in my group, taking data and turning it into sounds that we can hear. So sort of translating it. So anything that's traveling through stuff that's moving technically has its own kinds of sound waves. And we will be measuring waves as we travel through it.
I guess we should stop.
Okay. Can I answer one question?
Sure.
Dr. Young, my name is Z-E-O-S, and I have two short questions. In our galaxy, the planets,
Uh-huh.
9 or so, do all the planets have the most magnetic pole, say the north, the most magnetic pole, all of them are aligned in the same, say 1, 2, 3, 4. Do all of them on the top on one side?
Oh,
Is the sun the same way?
so are all the magnetic poles of planets and the sun aligned the same way? Well, not all the planets have magnetic fields, for one, and they're not all aligned the same way. The poles are also changing. The sun's poles change regularly over 22 years. Its activity cycle is 11 years, but actually every 11 years the sun's pole reverses, and then moves back over the next 11 years. So 22 years is actually the magnetic cycle, and then the activity cycle is embedded in that. The Earth, for example, has a cycle that's not regular, and its field moves over tens of thousands of years, and other planets do similar things. So they're all very different and very complicated. So the basic answer is no. The magnetic fields are not aligned.
And my last question, sir, I hope it is related. The Earth has 13 months, not 12, like the calendars we have around here. I'd like to know the ancient astronomers that had that calculation 13 months, and since when they decided, as the last few thousand years, I don't know, to make it 12. It is 28 days and a few hours. So since when they come up with 31 days?
Well, I mean, I will say that the calendars, the modern calendars, are the bane of our existence because they've made our lives so complicated because of the fact that the moon cycle's different, the sun's cycles are different, the star cycles are different, and some, bozo somewhere decided to pick a particular set of calendars that.
How long ago was it changed that?
I don't know when the Gregorian calendar and all that came about. When was that?
Well, we know that the Romans assigned a certain length of days to the months, for example. So August has 31 days because Augustus was held.
Why they came up with a number 12? I don't understand that. Why they try to change that?
It's a solar calendar versus a lunar calendar.
Yeah.
You're thinking lunar calendar, and
Ours is a solar calendar. I mean, but it is an incredible pain because of all these different systems. So the different periods don't line up, and they make things very complicated and interesting. So, thank you.
Thank you, Dr. Young.